Hello everyone, this is Susmita Das. Today I am presenting my poster presentation and the title is Effect of Reduced Graphene Oxide in Dysprosium Chromide Nanocomposite System. In this investigation, dysprosium chromide nanoparticles and dysprosium chromide reduced graphene oxide nanocomposite are synthesized by using a hydrothermal technique. When dysprosium chromide is incorporated with reduced graphene oxide, it is demonstrated up to 87% efficiency towards the photodegradation of rhodamine B dye, which is considerably higher than that of dysprosium chromide itself and commercial Degussa P25 titania particles. These two dysprosium chromide and reduced graphene oxide dysprosium chromide also exhibited excellent photostability and reusability. Here I have given the process of the synthesis of the dysprosium chromide nanoparticles and reduced graphene oxide dysprosium chromide nanocomposite. In brief, a fissile hydrothermal technique was employed to synthesize the dysprosium chromide nanoparticles. The graphite oxide was prepared by adopting the modified Hammers method and sonicated in deionized water for 2 hours to obtain graphene oxide. Graphene oxide was thermally reduced and incorporated with dysprosium chromide by the hydrothermal method. The structural properties of the synthesized graphene oxide dysprosium chromide and reduced graphene oxide dysprosium chromide nanocomposite have been investigated by the Rietveld refined power XRD spectra as illustrated in figure 1A to C, and the characteristic peak of RGO is observed at 25 degree. FESM images of dysprosium chromide and dysprosium chromide reduced graphene oxide demonstrated good morphology and crystallinity in the figure D and E. UV-visible spectroscopy is used to obtain the optical and photocatalytic properties of dysprosium chromide and reduced graphene oxide dysprosium chromide. High absorption is observed in the UV region after reduced graphene oxide incorporation. Band gap is also reduced after reduced graphene oxide incorporation. For assessing the potential photocatalytic degradation performance of the nanomaterials, the dysprosium chromide nanomaterials and reduced graphene oxide dysprosium chromide nanocomposites are subjected to degrade a standard dye rhodamine B under the irradiation of UV visible light in an aqueous solution. Time-dependent absorption spectra delineating the photocatalytic degradation of rhodamine B dye in the presence of dysprosium chromide and reduced graphene oxide dysprosium chromide is demonstrated in figure 3b. The photocatalytic detection efficiency of rhodamine B dye as a function of irradiation time, and the 3b shows the pseudo first order kinetic loss, and recyclability is shown in 3E of dysprosium chromide and 3F in dysprosium chromide reduced graphene oxide for 4 successive photodegradation of rhodamine B. And here we have seen the dysprosium chromide nanoparticles and reduced graphene oxide dysprosium chromide nanocomposites exhibited consistent photocatalytic performance for 4 successive photodegradation. The photocatalytic generation of hydrogen gas through the splitting of water was performed under solar irradiation. Figure 4 represents the amount of H2 evolution as a function of irradiation time for different nanoparticles and nanocomposites. Dysprosium chromide and dysprosium chromide reduced graphene oxide and commercially P25 titania particles are used as photocatalysts. Dysprosium chromide reduced graphene oxide also generated approximately 3 times greater amount of hydrogen via water splitting compared to that produced by the P25 titania particles. This figure is a schematic representation of photocatalytic dye degradation mechanism of dysprosium chromide with reduced graphene oxide incorporated nanocomposite. The hydrogen generation by water splitting is demonstrated by figure 5, a schematic representation of the mechanism of H2 generation. Under the irradiation of UV visible light, the dysprosium chromide absorbed the incident photons and generated electron and proton pairs. The generated electron in the conduction band rapidly transferred to the surface of reduced graphene oxide. The surface of reduced graphene oxide provided adsorption planes and active sites and inhibited the non-radiative recombination of electrons and holes. Concurrently, the photoexcited hole in the valence band reacted to hydrogen oxide and produces proton, which then reacted with the photoexcited electrons at the surface of the reduced graphene oxide and produced hydrogen. In conclusion, I must say that reduced graphene oxide dysprosium chromide shown a superior photocatalytic performance than compared to that dysprosium chromide and commercially available P25 titanium nanoparticles. This investigation is characterized by the solar energy harvesting potential of dysprosium chromide and reduced graphene oxide dysprosium chromide suggested that the incorporation of reduced graphene oxide with pristine perovskite oxides can efficiently improve their photocatalytic performance. Therefore, reduced graphene oxide based nanocomposites might be favorable for photocatalytic dye degradation and hydrogen generation via water splitting. The references are used in this presentation is given below. And that brings us to the end. Thank you so much for your time. Thank you so much for your interest and attention today.